Okay, we start our day 10. Okay. And today we're going to talk about the main topic for today and tomorrow will be oil and gas processing. And what I want is to give an introduction about, so you just have an overview. We are so far, we are saying we have our well, and we are producing, okay, we are producing to a separator, and that's it, okay? And we get here somehow magically, we get our oil and we get our gas. But in reality, it's a very complex process that has a lot of parts. But the reason why we can just use one single point here and don't look at anything else that is downstream is because here we have a fixed pressure. Okay, we have a boundary with constant pressure. That's why we can take all the rest out of the picture. The only thing where it is important is the oil-gas ratio. Okay, how much oil and how much gas you have. That depends on the surface process. Okay, so just to say also that if you're making an analysis equilibrium on a well, you have to include somehow the surface process, and that enters indirectly in the black oil tables. Okay. So even though you're not looking at it, you're just using a constant, a fixed pressure that is there somehow in the black oil tables. When we change from local to standard conditions, we always have to include the surface process. And if for some reason that's changing, you have also to change. Okay, that's sometimes I use a test separator. Okay, I don't know if I have a picture someplace. Okay, just a separator mounted on a truck. If I have to go and measure one well in one field, I go take the separator with the truck, I lower it, and I start to flow through it, and I measure. Okay, but the oil and gas that you're going to get from there is different than the oil and gas you're going to get from the real process. Simply because the test separator is usually simplified. You have just one stage, okay, and right away to standard conditions. In the plant, you will see now you have two, you have sometimes three, sometimes you have four for a reason. So, okay, so let's make a diagram. Instead of printing it, I decided we are going to try to make it together. Because then, if we write, we start to fix things on the brain. Okay, so let's say here we have to the left we have the well stream. Okay, and it can be one well to one separator. That's very typical in the U.S. In the U.S., for example. Or it can be that you have a pipeline transporting all the production to the separator. So the first step that we have is we have a box, okay, where we have, let me see if I get enough space, okay, we have what we call oil, gas, and water, separation, and stabilization. Okay, and that means first, the word says it, okay, separate. Exactly, this box is in the bad area, in the twilight zone. in the Triángulo de las Bermudas, Bermuda Triangle, you see, doesn't like separation and stabilization. Okay, and after that, I get exactly what I expect. I get one stream coming up, that will be gas. Okay, I have one stream, and we are going to put it to the right, carrying the oil. And then we have one stream coming down that has the water. Okay. And okay, and that's really the core. We are going to see that's a very important process, and we are going to spend a lot of time, or well, these 2 days, mainly on that process. Okay, I'm going to give you an overview. I'm going to tell you what do we have in each box, but basically we're going to focus, do calculation in this box, because it's the heart of the whole process. Okay, and it's something that we have to design very carefully. All the others are also very important, but it's not the main. It's not the main. So then after that we have a box, another box that we have the water treatment, produce water treatment. Okay, where the main purpose of that is to remove the oil that was left, and we're going to talk in a while how much oil we have left. Okay, we have some gas and we have some oil in this water that is coming out of the separation. So we want to take that to levels that we can do two things. Okay, we do two things with this water. We can either take it to disposal. Okay, that we can do to sea, to a river, okay, or we can do re-injection. Okay, that means for pressure support. Okay, now the oil, the same thing. Okay, the oil usually has some water content. So I typically have to do two things: oil dehydration. Okay, remove the water until you have some minimum amount. Desalting. Okay, because usually the water, formation water, is salty, so you get some salt in the oil. And then you have stabilizing. Sometimes I need further to stabilizing, okay? Because the oil that comes from here sometimes is suitable just to put it right in the tanker, and that's all, okay, or right in the pipeline. Sometimes not, okay? Sometimes I have to do an extra step to be sure that I remove some of the vaporizing component. And here, this oil, I can decide to send it by a pipeline, okay, that's very typical in the North Sea, or I can decide to send it by a tanker, that's very typical offshore, or a truck if we are talking about land operations that don't have a pipeline close by or that are, remote. Okay, very simple. We'll see that's very simple for just one box. Okay, for the oil, one box for the water, that's it. Now for the gas, it's a bit more challenging. The next step we have after the gas, after we separate, maybe this box is too big, we have dehydration usually. You're going to see that the water causes a lot of issues in the system. Among them, you have corrosion, you might have water accumulation, you might have, if it's low temperature, it will freeze, you might have many issues, so we want to get rid of the water. Then the next step after dehydration, I have to increase pressure. The pressure that it comes out here is usually not very high. Okay, so I have to use a compression station. Okay, to compress this gas. And sometimes here that gas just goes right away for re-injection. Okay, or it can go also to do gas lift. It doesn't go into that box, okay, it's just they are in the same place, but doesn't go to the oil box. So let's maybe make it here on the side. Okay, re-injection, okay, for pressure support. Okay, or for if you're doing some EOR, enhanced oil recovery, or you can also use it for gas lift. Okay, you can also use it for the auxiliaries for power generation. Okay. After that, usually also have, if I'm exporting gas, I have, it will come to another place, usually is the gas plant, okay, where I have a few processes that are made here. One of them is dew point conditioning, dew point control. Okay, well, I'm going to put them in the order. Okay, first is conditioning, then is dew point control. Conditioning means removing all undesired components that you don't want. Okay, so basically, conditioning, we are talking here about CO2 and H2S. Okay, undesired components that can cause a lot of problems later. They cause health issues, they cause corrosion, they cause. Then you have dew point control. And we're going to see a bit now what does it mean. But basically, you want to make sure that you won't have any condensation, either of condensate or condensation of water downstream. Okay, so that's the main purpose of dew point control. And then you have NGL extraction. Okay, what NGL stands for? What? NGL. Okay, natural gas liquids. And that color is not a good color, so we're going to put it green, okay, because it's like a natural gas liquids. Okay. And after we have that already dry, then you can use it for sales, okay, or you can also use it for another, maybe in case there is an LNG plant. Okay, and then you go with a tanker. Okay. So that's basically everything we do with our oil and gas and water. Okay, these are more or less all possible destinations and all possible processes I have. Okay, the oil after that, I go to a refinery. The gas, either I sell it for power generation or I take it on a tanker. Okay, yeah, and water I just re-inject.
Second square on the gas power generation. In that part is power generation for the well, used all for other things.
Yeah, here I refer, that's for the facilities, okay, for the field. Okay, And that's very, here I'm mixing a bit, but you have the same process offshore and onshore, okay? But for offshore, this part is very important, okay? For onshore, you sometimes can get your energy from the grid, so you don't need to generate, okay? Unless you're in a very remote place. In our case, offshore, we always need to use that gas to generate power.
So it's common to use gas in power generation.
That's what you use, yeah. Mainly gas. Okay. If that's clear, now let's start to put some numbers, okay? And I'm not sure if I will have, maybe I have to lower these guys down just to get some space. Okay, because we are going to start to put some numbers so you have an idea what are we talking about here. Oh yeah, so one more thing. What we have offshore, I don't want to spoil the figure, but let's see how we do it. What we have offshore is usually, I'm going to put it in a black. Okay, offshore we have all of that down to here, all of that up to here usually. Okay, that's all we have in an offshore offshore field. Okay, you might have all of it, but only if it's onshore. Usually because this guy takes a lot of space, and you don't normally do it in the on the platform because it takes a lot of space, and then the cost will be just too high. Remember, offshore, the weight is one of the driving factors. Okay, the weight. So if you have a very heavy process, you have a lot of things you want to put there, that's going to increase dramatically the cost. Okay, so let's see, the well stream here, the pressures that we have in the separator, they can change very dramatically, okay? But usually between, and here I'm going to make you happy, I'm going to write in field units, okay, 800 psi all the way to 750, okay, or maybe less. But those are, and we are going to see now what affects that pressure of the separator. 1800 is quite high, okay, it's like 130 bar, I think. So it's quite high for a separator, but we are going to see what defines that. So the oil that comes from here, typically it has water in oil of 1 to 3% in volume. Okay. So then I have the dehydration process, just to make sure that I take it down to normally what I use or what I need for transport. Some places this is water in oil. Okay. Sometimes I need a number between 0.5 or 1. Okay. It has to be around that value. So I'm using that's the maximum I can get with separation. And separation, we are talking about these vessels. We are going to see now some pictures, but that's the maximum I can get, between 1 and 3%. Okay, that depends also, if I make it bigger, it has more time to separate. Okay, but if I put it bigger, it's more costly and it's not good for the economy. So then I have dehydration to take it down to 0.5 to 1, and that's what I need to avoid corrosion, scale, all kind of issues. Or if you're in Norway, we are using 2%. Okay, we're using a slightly higher, let's put it here, 2%. If you're in Norway. APIs that we are talking here, APIs can be anything from something very low, 8 API, 8 all the way to maybe 60 something, okay, 65. That's very, you can almost put it right away in the car. Stabilize, when we talk about stabilize, I told you, you don't want to vaporize when you have it at atmospheric conditions. So you use, that probably you have heard before, the, vapor pressure, right? So just to make sure, if you're in a tanker or a truck, okay, you have to be below, at least below 11 psia, the vapor pressure, okay, which is like the vapor pressure of the fluid at a given temperature. Okay, usually temperatures are around things like 38 Celsius, something like that. And they call it read is the way they measure it, okay? They cannot really measure just with the oil by itself, but they have to put it in a chamber which has also air. Okay, so the measurement they get from there has the effect of the humidity of the air. Okay, so that's why it's called read, okay, instead of true vapor pressure. However, if you are transporting on a pipeline, okay, then you can relax that. It doesn't have to be so strict, 11, but it can be all the way to 111 psi, and here sometimes they use RVP. The salt content also you have to be, that's why we need sometimes to dissolve. Salt causes corrosion, causes also mineral accumulation. So the salt content has to be something between 10 and 30, and this is pounds of 1,000 per 1,000 barrels. Okay, this is pounds. So here you see we have a mess of units, but I guess you are happy. You are seeing some field units for the first time in the course. Okay, and something very important that we have to take care. So these are all the things that I say, these are like export specs. Okay, the specifications of the crude that I'm exporting. The API, okay, very important. Not every refinery takes everything. So you have to be sure that to the refinery you go, they accept the crude. Water, mainly for transportation. Okay, I don't want that it will start to have corrosion on the tanker, on the trucks, whatever I'm sending it, the pipeline. The vapor pressure, okay, is important, and I measure it with this number, the read vapor pressure, 11 or 111 if it's on a pipe. The salt content, between 10 and 30, again to avoid corrosion. And then the last point is the H2S content, okay? That H2S is very poisonous for humans, okay, this gas, so we have to be careful. So for fields, that's one of the questions. You're traveling to the field, you have to ask if that field has H2S. And if you go to the field, you go to the wells, usually they give you a meter where you can measure the H2S content. Okay? And if it starts going up, you have to run. Okay? And this number is something between 10 to 100 ppm in weight. And I can reach usually that number in normal separation. Mainly, most of the H2S goes to the gas. Okay, it will vaporize to the gas. So that number is usually not a big problem. Okay, now we go, the gas we leave it for later. Okay, gas is always a bit more complicated. Water, this water that I have here coming from the separator, normally it has a number like between 500 and 1,000 ppm, and I think this is on weight. Okay, this is oil in water. Okay, so it has that amount of oil that I cannot separate with a normal big vessel separator. So then I have to use to treat. We're going to see now the equipment. We have different options. And for disposal, water or river, I need at least less than 40, okay, less than 40 ppm oil in water. And this is ppm in weight. You have to be less than 40 ppm. Yeah. So we can put it like this, just to be consistent. It's the same, but you have, depends how you, if you read from right to left or left to right, part of the world reads from here to here, part reads from there to there, so it's confusing. Okay? But it has to be 40 ppm. If you want to throw, you add a platform, or you want to throw to a river, usually you have to have below 40 ppm. Reinjection, you have slightly higher. I think the number is around 100. Okay, but the main problem with the reinjection is that you can plug the formation if it has too much oil. Okay, you start injecting, and this oil starts to accumulate in the near wellbore region, creating this skin that we spoke, right? And then eventually you won't be able to inject as much as you had initially. So you have to either refrac, or you have to drill another well, or all kind of solutions. Okay, and here I just want to emphasize, sometimes it's very difficult to get this number. So that makes that you cannot process that much water that comes here. Okay, remember the discussion we had yesterday. With time, usually the rate of water, or the water cut versus time, is increasing, okay, very like that. So when you are at the late stage in the field, these facilities will need to produce or take a lot of water, okay? And if for some reason the time is not enough to get to this requirement, you have to reduce the rate. But you cannot just reduce the rate of water. Okay, you have to reduce everything. Water comes with oil and comes with gas. So if you have to reduce the rate, you have to reduce the whole rate of the well stream. Okay, and that's when you say my facilities are bottlenecked. Okay, facilities bottleneck. Okay. So fairly simple, right? For water, oil in water, and for oil we have a few things, but no big problem there. Now let's talk about the gas. And the gas, mainly the main difference comes in. We will see this is some gas that is. It still has a lot of condensate, okay? Still has a lot of things of heavy or not so heavy, but heavier than methane components that you can take out from this gas, okay? That then can condensate from the gas. But the main issue here, the first one, is dehydration. All of this water that the gas has, remember the discussion from yesterday, the formation gas is saturated with water. Okay? And when you start reducing the temperature and pressure, this water is starting to come out of solution. Okay? It's starting to come out of the gas, to condense, to drop off the gas. So we take that first, and then we would like to do that here, because this guy before the compression, because then it will make my life a lot easier. But I cannot because of the size. So I compress, and then I send through the pipe. And yeah, so this is usually called yeah, I have the name here. It's called rich gas or wet gas, rich gas pipeline. Okay, and rich because I haven't taken yet any of these components. Okay, I haven't taken any of these heavier hydrocarbon. The pressure that we normally use depends a bit on this place, but it's something that can go between 80 and all the way to 200 bar. Okay, we went back to SI. Okay, but very important, the minimum water dew point that I can get. Okay, so the water dew point with the dehydration. We're going to see now how it is, but it's basically using TEG. Okay, T3-ethylene glycol is at minus 18 at 69 bar. At 69 bar. Okay, so what does it mean? If we look at the phase envelope of the gas, P and T, and you remember we had very small and then the whole big section of gas, okay? That means if you take this at minus 18, you should have 69 bar or a lower pressure or a lower temperature. Okay, so it will take, if you have the gas at 69 bar, it will take you to go down to minus 18 to start to get some condensation. Okay, that's the minimum that we can get with this dehydration, TEG dehydration. Then we have the water content. Okay, the water in gas typically has to be something below 4 pounds per million standard cubic feet. The CO2 content is very important. If we cannot reach or agree, we cannot match the CO2 limit, we have to include the conditioning before. Okay, so that's extremely critical. If your field has too much CO2 or too much H2S, then I have to include conditioning before, and that's very expensive. Okay, I cannot wait to do it on the plant. So this should be below 2.5 mole percent. Other things that we have to care is also H2S. So let me bring that line down. I told you gas is always misbehaving, okay? We have a bunch of things to look at for in gas. H2S also less than 5 mole percent, okay? And then we have two other criteria related to the envelope, okay, of the gas, and they say that the Criconden term should be located at below, I think there is a mistake here. It says 40. Yeah, 40. I have to check this number, okay? But Cricon and the Criconden bar has to be 105, less than 105 bar. Okay, and that basically is another way. Here on the dew point, I'm specifying, it has to be below that, but it can be that my envelope, for some reason, is doing something like this. Okay, so therefore, I use the Criconden term and the Criconden bar, okay, just to say to limit the size of my envelope. Okay, such that in the transportation process in the pipe, when I change pressure and temperature, if for some reason I ensure that under no conditions I will have a significant amount of condensation or no condensation from the gas. Okay, then we come to the plant, okay, and in the plant is even more strict, the limits we have to sell the gas. This is the gas that we get in our homes or you get when you, this is the gas that is used for power generation, and here we have So a bit more strict. So the dew point has to be -10 at 50 bar. Okay. The water dew point okay, I have to take it down to
So I didn't understand why are you using relative pressure instead of absolute?
yes, I'm not sure why. I think I made a mistake here. I'm going to take that away. Sorry, what?
Why these conditions are given with relative pressure and not absolute?
Well, no, these are absolute, but these are, I'm not sure why, because some people like to work in G. That's how it was on the literature. Okay, I didn't change it. It doesn't look nice if I say 201 bar, but it looks nice if I say 200, right? So I think that's the reason why, just to make the number look nice. Okay, I think. Okay, dew point, but here I have other things. Again, the CO2 content has to be, again, less than 2.5 mole percent. And the H2S, again, less than 5 ppm. And here I have to take care of other things. We have the calorific value and the Wobbe index. Okay, because when I burn this gas goes directly to the power plant, okay, and it goes directly to our homes. So when we burn this gas, we want to make sure that it's compatible with the burners we have. Okay, it cannot happen that I start burning in my place and then it will start basically the stove cannot tolerate that amount of energy because it maybe has too much rich components. Okay, so I have to make sure, and for that I do a bunch of other things. Okay, we are going, as I mentioned, we are going to look mainly in this drawing into this guy here, but I just wanted to show you the whole figure, and really is just to take these products to specs, okay, to take all of that to the specifications that I need. Okay, for gas it's very important the envelope, to limit the envelope, mainly for transport. Okay, it's important to limit the amount of energy it liberates when it burns, later if I put it on the pipe. The H2S and, sorry, not H2O, H2S, okay, I don't want these gases causing issues on the pipes and not health issues for the people. And then oil, the water content is important, salt is important, API, very important, and water, basically just the oil content. Okay, so I'm going to write something here just before we leave this, just to see what kind of technologies do we use in each part. Okay. Okay, for oil, gas and water separation, I use typically, we are going to see now, is a multi-stage separation train. Okay, and multi-stage, we have one main separator, but we go down with as many, some places they have even 4, okay, 4 stages. If you can do it in one stage, that means you're almost separating almost directly to standard conditions, or 4 stages. We're going to see now how it looks like. And typically, trains we can have, if you're onshore, we can have as many trains as you need. Okay? If you go for a very big separator, this will be very expensive. So sometimes it's better to buy a bunch of small separators. Okay? Offshore, we don't have that privilege. So normally we use 2 trains. Okay, it's very common. So multiple trains as needed. Okay, this is onshore, but offshore we use something between 1 and 2 trains. Okay, because we don't have space to put one next to the other. We prefer to pay a bit more, but to have a big vessel. And here we are going to look at that. That's why you have this drawing there. But you have, typically we have interstage cooling, okay, and interstage cooling and compression. So we have some compression in between, and we are going to see why. But basically we are taking out gas from a low pressure, and then we want to merge it with a high pressure. So that's why we need compression. Okay, then we go to the water. Okay, we had water, so it was treatment. Oh yeah, maybe I can show you some figures of, we have to put some color to our slides, right? Okay, so that's the separator we use for oil field. We use a separator, that's a schematic. This is actually from somebody here working with the processing plant? No? Okay. And the separator, this is a three-phase separator, okay, and it's horizontal. So this is three-phase horizontal separator, okay, where you see the gas goes to the top. I have a few things here that I will make a comment briefly what it is. The oil goes in the center, and then you have a weir plate where the oil is just overflowing through it, and gas is just stay here. Okay. And not all separators are three-phase. Many of them are two-phase. But usually the main, either the first or the last separator are three-phase. Okay. These devices here are, so I think I have another figure a bit better. Okay, that's a horizontal separator. Oh, I had another figure, which was, okay, it's here. Yeah, it's behind the okay. So initially you have a diverter, you have also momentum dissipator or momentum generator, and it's basically something to change the direction of the stream that comes. Okay, you don't want the stream to be, let's say if you have a stream of fluid entering the separator, it will have high velocity and it will create a lot of mixing. Okay, by breaking momentum breaker or momentum absorber, they try to break to reduce that energy, that kinetic energy, and also to try to separate. In the heat, the water, the liquid sticks to the surface and starts to slide down, and the gas just bypass and goes. So you have separation, and you try to eliminate that kinetic energy. Then you have these internal baffles. Sometimes they have it for, if you are in a vessel which is moving, okay, you have waves. You might have formation of waves. So these are just to break and also to enhance separation. Then you have these pads, okay, which are the misting. These are mainly, the main function is to remove the droplets of oil or gas or water from the gas before the gas is coming up. Okay, and this demister, okay, it looks something like this. Okay, we make just a mesh. There are different types. Okay, one called with plates. Okay, or one with some mesh. Okay, you put a mesh right very tight, and then the gas has to flow through it. When it passes, it has to change direction, it has to impact many of these metal, and then the liquid starts to drip down. Okay, I think that's all I had. Do you want me to paste the figures here so you have it, or not?
Yes.
Yes? Okay. But then don't come if someone comes and say, well, that was my figure, so I'm going to say I don't know anything. That my students, they put the figure, okay? Okay, so that's how it looks like with all the things outside. That's just in a facility, but when you put all the things, you can almost not see the separator, depending on all the things you have. Okay, then the next step that we have was the water, okay, the water treatment. Okay, and water treatment, we typically onshore, we use skim tank. Okay, that I think I have a figure later. We sometimes use skim tank, and sometimes we use degassing. Okay, we have to take out the gas that the fluid has, and this is the most common onshore, where I have space to put a big tank, and we are going to see the process. It needs a big space, and oil goes. It's very similar to the weir plate, okay, where oil goes at the top and starts spilling out from the top. But in the platform, okay, so this is very typical onshore. In platforms, we don't have that much space to put a big tank of water. So what we use hydrocyclones, okay? And hydrocyclones, we use very high Gs, okay, very high rotation of the fluid, and then that makes the heaviest fluid, the water, to separate, go to the walls, and the oil stays in the center, okay? And they are used basically because they are compact, okay, and you can achieve the same result. And on top of that, sometimes we use flotation unit, gas flotation unit. Okay, and I think I have a figure of that. Let's see. Okay, so that's a skim tank, this guy here. You have almost no gas, but it's very similar to a separator. You see the oil, you have a very fine layer of oil flowing at the top, and then you're skimming that oil out, either by overflowing. There are all kinds of methods. And let's see, the flotation unit is here. Okay, flotation unit, basically I inject some gas, some bubbles with the liquid, that the liquid has water and has these small droplets of oil, and the gas just starts to trap all of these droplets of oil and takes it to the surface. They stick to the surface of the bubble, of the gas bubble. Okay, so very boring, not much to see here. Then we go, what else are we missing? We have separator, we have, and now comes, so we have seen this equipment, we have seen this equipment now here. Okay, and okay, the dehydration, okay, oil dehydration, that's what we call it, right? Oil dehydration. Desalting, okay, is sometimes made with an electric coalescer. which is an equipment that uses a lot of energy. And I think I have a figure here someplace. Okay, that's a model which is very nice. I'm not sure who made it, but I'm going to copy. Okay, you have due to the almost olive oil, right, who has no, how to say, has no polarity, okay, has no magnetic charge, except for the small droplets of water. So you subject the water to an electric, to a magnetic field to induce that polarity, and they start to get together and they start to float towards the top. Okay, and the inlet, yeah, in this case is here at the bottom, and the oil comes from the top. The desalter is basically very similar. Okay, it's very similar to this electric coalescer. But I have to get fresh water, okay, water that has no salt. I have to mix it with the oil, which sounds weird, right? I have to add water to something that I want to remove water. But I mix it such that that water takes a lot of the salt that is in the oil. And then I use again, once more, this electric coalescer just to separate. Okay? And it's not much water what I add. It's sometimes between 4% and 8% of fresh water. The stabilization of the oil, that's not something normally we make offshore, but onshore we do it by heating. Okay, you have to heat the oil, like to cook it for some time, such that all of these gases, they come out of solution. Okay, now let's go. We are going to be soon, well, not soon, but we still have a few things. Now we have the gas, okay? And for the gas dehydration, almost very few places we use something else, and we use a TEG coalescer, a TEG contactor. Okay? We use a substance which has a very good affinity for water. Okay? And the process we make is, did you cover that TEG contactor? When you, who is chemical engineer here? No chemical engineers? 3? Yeah, okay. So that's why you're not making noise. You're only, and all the rest, what are you, mechanical engineers or no engineers, accountants? No? I have no accountants in class, right? Otherwise, I guess you're having a hard time.
This is treatment micro, as you said.
Yeah. Okay. So a substance which has a high affinity for water, so we flush the gas through the column. We have some trays. Okay, these trays are filled with this glycol, and the gas is entering through here, passing through the liquid, and then going through the next tray. Okay, by doing that, it has a lot of contact with this TEG, and then it takes out the water from the gas until it goes out. Okay. Then I have here some other process that I recycle that glycol. It's not I can throw it away, but I have to recycle it. So I have to get back with reduce the concentration of water in the glycol. Okay, but that's the key. Usually this is the process I use because it's very efficient and it's expensive, but it's very efficient. This usually has to be run at high pressure. I think the pressures of these guys are around maybe 800 to psi, and here we're going to say G, I think, yes. And the temperature of the reboiler is something around 400 Fahrenheit. So it's a process that needs a lot of energy just to regenerate this TEG. Okay, then we have one more process to cover, okay, before we go to the fun part. Okay, here the conditioning, where you remove CO2 and H2S, dew point control, so let's put here gas plant. Okay, so they call it sometimes DPC. Okay, hydrocarbon dew point control. Okay, and I have a few methods that I can use for that. Okay, one of them is called JT expansion. Okay, basically is Joule Thomson expansion. Okay, what does it use that process? Exactly what we discussed with the choke. Okay, you remember I have an isenthalpic expansion. What happened with the fluid when I reduce the pressure in a choke? If you remember with the temperature, a drop, right? We had a very drop. In our case, was not so big. I think it was a few like 30 Celsius or something. But you can get, if you have a very pressure drop, you will have a very high drop in temperature. Okay, and with this drop, then you get a lot of the liquids. Okay, the condensates, water, etc. So this is just valve expansion. And Joule-Thomson is the name of this phenomena that in a gas, when you reduce pressure, also the temperature drops. Okay. You have it also in a pipeline. In a pipeline, it might be at the inlet, the gas is 70 Celsius, and after that, after a long time, it might come even lower to the temperature of the ambient, okay, just because of this Joule-Thomson effect. Then we can also do it with a turbo expander, okay, where it's not anymore, this is isenthalpic. Okay, this is not anymore isenthalpic. Okay, this is like a turbine. So how do I make a turbine? A turbine is like that, okay, enters through the small part, 2. Or I have also some other processes that are a bit more expensive where I have refrigeration. Okay, I basically have to cool down to very low temperatures to start to, that the liquids will drop off. Okay. And then I have another process which is, here I can also make some recovery with all of this process. I can recover some MgL, okay, but I have also NgL fractionation. Okay. Well, before that we have demethanizer, okay, and NgL fractionation, which basically is a process, is like a distillation tower. Okay, where I have different trays with different temperatures, and at each tray where I have an output, I have the temperature of certain product. Okay, I drain propane, butane, and I do it in this. We are not going to talk about that too much. So, chemical engineer, you have your eyes open. You say, "Wow, I like it." So, we're not going to talk too much, petroleum engineers, but just to make you aware of that. Okay, so now let's go to what will be our focus now. So now that you have an overview, okay, more or less you know, all of these equipment are really, we have it in place just because of these constraints. If we could take oil just to the plant, the way it comes from the well, we will do it, okay, but we cannot. We have to transport, we do it in tanker, we do it in truck, so we have to fulfill all of those constraints. Water will be very nice if we can throw it away just with 500, but we have to have those constraints. The same thing with the gas. Okay, so let's go now to the main core, the heart of this process, which is multistage separation. Okay. The main objective is simply to separate, right, separate oil, gas, and water. That's the main purpose. Now, a secondary purpose that people don't talk too much about it, is to increase the amount of oil that you get from the stream, okay, from the well stream. And we are going to talk about it just in a while. Let's leave it for now, but you have to think, like, remember we had this GOR, right? We had this oil together with this gas that come from the reservoir. And we pass it through a surface process. And this surface process now is very complicated. Okay, this house contains many different things. But in terms of calculating the GOR, we can say very well that this is just, we can neglect all the rest. Okay, we can just say this is just this multi-stage separation. It's really what drives this GOR. Okay, is Q, G and QO. And if you use a different process, I'm going to get a different GOR. Here we're going to see that right in a while. So I want to choose the process that allows me to get, what do I want more? More gas or more oil? Why? Because you can sell it more expensive, okay? If you have the same amount of mass, you sell it as oil, you get a price. If you sell it by gas, you get a lower price. Okay, so the main is to basically reduce the GOR. Okay, that's our goal, to reduce the GOR by using a process that allows for that. Okay, so multi-phase separation looks like that in a very generic way. We have, okay, let's say now we have just two phases. Let's take the water out, focus on the two living ones. Okay, and here we go finally to stock tank, okay, and finally here we go and we take our QO. Okay, I'm making space just to put all the equipment we need in between, and here we have from the well stream. Okay, and I call this will be the HP, high pressure separation. I have MP, medium pressure separation, and LP, low pressure separation. Okay, pressures, they change a bit from country to country or from place to place, but high pressure, that's the number that I was talking about here before. Okay, this 1800 and 750. That's the pressure of the separator. But in a very small field, you could try to lower down. It can even go to 4 bar. Okay, it can even be very low. But for offshore, this is something between HP's 120 all the way to maybe 50 or maybe 35 bar or bar G. What do we have in between these separators on the liquid line that I have painted here? Not compressor, but I have a pump. Okay, I typically have a pump, and I have, of course, a valve, right? So I have the valve to control. Okay, now you can look at to get some tips, you can look at your drawings that you have. Okay, and I have pump. So I have a pump usually on every, and it sounds like a trivial thing, okay? You have a pump to move the fluid, but actually it's very important where you place the pump. What happens if you place the pump in a higher level, higher than the separator? We require that's one thing, but what happens with the available pressure at the inlet of the pump? Here, the fluid I'm taking here is exactly a saturation, right? When I take the phase envelope of this fluid, okay, I'm exactly here. Okay, so let's say it's an oil. Okay, so let's say I'm exactly here, right? So it will be, if we look at the gas, just P and T, okay, if we look at the gas that comes out, the gas, this point will be on its dew point line. Yes? It will have another envelope because it has a different composition. One, so here I have, this will be 1, this will be 2, and this will be 3. So this is the envelope of 1, okay, both. The envelope of 2 will be the dew point. The dew point will pass exactly through this point because the gas is on the dew point. And for the oil, for number 3, the bubble point maybe will do something like that. Okay? So this will be the phase envelope of 3. So any further reduction in pressure I make on number 3, what will happen? To take it to the pump. Okay, it still has to go all the way to the pump. So it has some pressure drop in that pipe. Okay, so if I put it high, the pressure drop will have to climb up and gas will be liberated, right? I will start to come inside this region. Okay, if gas is liberated, that's not good for the pump. Okay, so usually that pump I have to place it lower, okay, just to get some positive NPSH. Okay, and then I have another pump here. Okay, so that's very critical. Offshore is very simple to make. Onshore, we have to dig a cellar and we have to put the pump down, or we have to make sure that we don't get any vaporization. Okay, remember that also it's not only at the suction of the pump, but just you have another pressure drop when it gets to the rotor. Okay, you have, if you plot the pressure in the pump, okay, you plot the pressure, and here you have a pipe with the distance, and here you have the impeller. The pressure here is declining, 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 and when you enter, you have a sharp drop, and then you have a jump, and then you have the discharge pressure. But you have this local pressure reduction is inside the pump when it takes all the way to reach the rotor. The rotor is when it's going to get energy, but it has to get there. So it has this local reduction in pressure. Now, for the gas, what should we do with the gas? Well, the gas, we have to take it to the dehydrator, right? According to this plot here. We have to take it to the dehydrator. But we have an issue. The issue is that all lines coming out from the separator, they have different pressures. Okay? And there also another thing, okay? They come, what happens with that gas? Okay? It's exactly at the dew point. So if I lower the pressure a little bit, I will start having droplets of liquid, condensation. Okay? So what I do two things. I put a cooler, okay? Just to try to drain a bit more from this so I won't have problems later. So I put a cooler. Then I use a scrubber. Okay, so that's a cooler. Then I use a scrubber where the liquid will be accumulated at the bottom and the gas here at the top. Okay. And then after that, I can ensure that it's dry enough so I can send it to a compressor. Okay, and this will be the high pressure compressor. Okay, and this gas goes to, where do we send it? I think we have, okay, that goes to the dehydration, but Yes, but let's see. We are going to finish tomorrow, so don't worry. You're going to have time to rest. When I leave, you have time to rest. When not, you know, you.
Big fan. Can you please meet
Huh? I'm leaving soon, so don't be. I know you're going to be happy when I leave. Okay, you're going to be happy. Okay, to dehydration. So we have. So what do we do with that liquid that we get here? With this liquid, where do we send it? No, this is oil, right? What is condensing from there is mainly oil. I could use a pump, right? And then I send it back here because now the pressure is less. Okay, to pass through the cooler, you need some pressure drop here. You also have some pressure drop, so you can use a pump. Or if I don't want to use a pump, I just send it here. Okay, just let me see, send it here. Okay, it still has high pressure, so I can just send it with to the medium separator. Now, what do I do here with this gas? Exactly the same thing. That gas is exactly at the dew point, so if I reduce the pressure even more, I'm going to get liquid condensate. So I put a cooler, then I use a scrubber, then I use another compressor. So you see, even though we said there are no compressors, okay, we need to, and where do we send this guy? No, usually to avoid using too much energy, because that change is very big, okay? Delta P in compressor, the delta P, it's what drives like the power, okay, that it needs, and the, you know, how big is it? So what we do normally, we say, well, let's the medium compressor take care of it, and I'm going to connect it just here, okay? So maybe let's make it a bit nicer. Just don't be confused now with all the lines. Okay, so I connected exactly before that cooler, and then I can just, it will go through the cooler, the scrubber, and then that compressor that has to reach less pressure, okay? It has to reach from high pressure to this line, to the dehydrator, that I told you is like 800. While here, it just has to go from medium pressure to high pressure. So it has to use a lot of volume, but the delta P is not so much. Okay, so then I have here my scrubber. What do I do with that liquid? To the low pressure separator. Okay, so it comes here. And oops. You know, not everything is perfect with this method. You get some. I lost. Yeah, maybe it's better to remake that figure. Do you need it or?
No.
This one not? Okay. You are the class responsible. Okay, so I connect. I'm going to be finished soon. So you connect, and then you connect here. Okay, and then the last one exactly the same. You have a cooler to take out the liquid. Then you have this scrubber, 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 and then you go to a compressor, and then with that compressor you go and you send it here, and the gas. Oh, something that we didn't talk. So why do I call it scrubber? Or why, here all the separators are horizontal and this guy is vertical. Why is that? And here usually yeah, I'm not sure. I don't think it goes. It goes, I think, in front of the LP. I think so. So something that we didn't mention, and we should have made the comment, is that this is for oil, okay? When I have a lot of oil and when I have a little bit of gas. When I have gas, the opposite, that is the Christine, the one that is called Christine, I have another type of separator that is used, that is called, vertical separator. Here?
What avoid fluids to go up to disturb the pump there?
What avoids the fluid to go? The fluid to come here, to the scrubber.
No,
from the scrubber?
Yes.
From here?
Yes.
Well, the pressure, that's very low pressure, but the pressure of that line should always be a bit less than the pressure of okay, when you go from here to here, well, let's say here, from here to here, this pump is has a very low pressure drop. It's just to carry the fluid from this separator all the way to the low pressure. But this pressure is still lower than this pressure. Because it's gas, it doesn't lose pressure so much, okay? So this pressure is closer to the medium pressure, and therefore is still bigger than the lower pressure, and therefore you always have fluid on that. But you are correct. A good engineer, what do we do to avoid any problems? We call one-way valve, okay? But we don't want to overload the figure, but that's a very good point. If I want to avoid sometimes malfunctions, something happens, I want that this won't go up. Okay, so what happened with the hand? Okay, so let me just make the comment on that I forgot, okay, of the vertical separator. That's what we use for gas. We don't use that separator, and it looks like that because the amounts of oil and water, they are less, and it's more important to separate. Came everything together. Yeah, I think it's one figure. So. Okay, and this is a bit different. You want to have gravity, right, to help separating. And also you have these baffles in the center that you see when you see from the top, the effect, they deviate the gas, and then the liquid just sticks to the walls and they start to go down. Okay, it starts to, and here you have this demister, which is, this compound of mesh, the metallic mesh that we showed before. But it's vertical, it's like a small, so the scrubber is like a small vertical separator. Okay, now let's look at the figure you have, okay, of the two fields we have. One is an oil field and one is a gas field. Let's look at the oil field first and see if we can identify everything that we were discussing just now. Okay, where is the well coming from?
Sorry?
Where is the well coming from? Here, okay, from typical TLP well. So this is for TLP, stands for tension leg platform. It's a type of platform we have offshore, okay, in which let's paint the sea. Then we put some okay, we have our platform, we have our separator on top of that platform. But the way that platform is so how do I paint the soil, something like that maybe. Okay, I use tension cables to bring it down, okay, and it's positively buoyant. If these cables, so for some reason, are broken, the platform will go up. So I put those cables, I drag it down, okay, until there is tension in that platform. And the way it works is that if the wind, for some reason, moves the platform to the right, okay, the cables will start to make a force opposite direction, just to bring it back to the same position. Okay, so that's the principle of this TLP, and this is for TLP. I think this is for one called hydrogen. So where do we have? So where do we have the first, second, and third separator? High pressure, low pressure, and medium pressure, and low pressure. Where do we have the high pressure, low pressure, medium pressure, and low pressure separator? Okay, very easy, right? Here you have first stage, second stage, and third stage. Okay, and here we have that the fluid comes, we have a production manifold, okay, which is, I told you, just a section of pipe, and then we send to the first stage from the well, okay? But if you see, I have to test this well, okay, somehow. So you see that you have another separator, which is smaller, that is the test separator, and it's in parallel to the high pressure separator. So I can decide, depending which valve is open and closed. So what is the color? Do you know the meaning of the color? When it's full, it's closed usually, and when it's clear, it means that it's open. Okay, so this well is producing to the main production, and this I call the main production train, separation train, the three. Okay, or it could go to test if I need to test the rate of that well. Okay. You see, I have a collection. In that case, this vessel somehow has oil is drained from the two sides. Okay, so I have maybe the entrance is on the center and the oil flows on the side, and it goes over the weir plate, and then let me make just a simple sketch. Okay, we have the weir plate here. We have the water is being drained from here. Okay. The water is being drained from here. The water is up to here only. And then you have oil, which is just flowing through here. Okay, and then you have on top, you have the gas. Okay, so that's very likely why you have that diagram. Why? Okay, so you have here Q oil from here and Q oil from here, because the inlet is not on the side, but it's on the front. Okay. So let's continue. So here you see you have the choke valve. Okay, you have here the choke of that well. Now let's follow. What do we follow now? Let's follow the water first, okay, which is slightly simple. The water goes to the water process, to the water treatment. And water treatment in that case is, I don't have much space, it's very compact, so I use this is the symbol of a hydrocyclone, okay? It enters tangentially and it has a very high rotational speed. And where that goes here? To EPCON CFU. What is that? What did we have? Combination, hydrocyclone and flotation, right? This is where you introduce gas and it flows up and it takes out the bubbles. So this CFU is compact flotation unit. I'm not going to write, but if you want, you can write okay? If you want the acronyms. Compact flotation. And you see you have one hydrocyclone for the test, we have one for the medium, and we have, here we don't have one, Okay, but we have for the medium and we have for the test. For every separator, we have its own cycle. We don't want to be pumping at high pressure and then send it to the same cycle. We want to split like that. Then, okay, so let's see, between them we have test separator pump. So here we have that pump that we were talking. I think, okay, on the oil, okay, so let's see what happens with the oil. The oil goes to the crude transfer pump, a cooler, okay, and then the metering, and that's it. And then to export. So here I had no need for, and it's usually like that in the North Sea. We have no need for dehydration or no need for desalting. Okay, 2%, it's enough. Okay, some other places in the world, they have to have the coalescer. Okay, we don't have it here. Now what is left is the most complicated always, which is the gas. Okay, so let's follow maybe the gas from the high pressure. Okay, so you have two ways. One, it goes to flare, and that's normally when I have an emergency, like an overpressure. I always have a relief valve, and that goes to the flare. And that the flare is usually far away from in the platform is this thing sticking out. You have seen it, right? Okay, you have something. Okay, usually you have like a long thing, the boom that is sticking out, and here you have sometimes it's on. So when I have an undesired event, it just sends to the flare. And then I come and I have a cooler, and then I have this famous scrubber, and then I come to a compressor. Okay, and it's the first stage. Okay, so the first stage comes to dehydrator. Okay, right away. So I come here, I have my dehydrator, and I send the glycol, the clean like glycol, not much water from the top, is going down, and then here it comes. That's why you have the change of color. Okay, you have rich glycol, and then you have lean glycol at the top. And then that goes to, before compressing, the pressure is enough to use it for turbine. Okay, here at the top you see fuel gas. And then I need to compress, and I send to many different things, okay? So goes to gas injection well, goes to gas export, another gas export, it goes to gas lift for a production well, and gas lift to riser, okay? So here another small clarification. When we have we normally have a pipe, okay, which is called a riser. Here I have all my wells. I gather the production with a flow line, and then I take it with a pipe that typically has this shape to the boat. Okay, and sometimes the pressure drop, this could be, I think in hydro, I'm not exactly sure, but I think it's around 300, 200 meters. And this pressure drop can be significant. You can be creating a lot of back pressure on the well. So what you do is that you take, just like in a well, okay, you send out a gas line and you inject it at the base of the riser just to reduce the column and to reduce the pressure drop. So it's like applying a gas lift on a riser, okay, on a pipe. So this is riser base gas lift. And that's it. Okay, so I'm not sure, maybe we could go through the medium separator. What is the okay, second stage, we go first to cooler, then we go to scrubber, then we go to compressor, and then we go to the cooler of the high pressure. Okay, so exactly the same. You have to know how to sketch it. Okay, if I ask you in the exam, hypothetically speaking, okay, draw the multi-stage separation process of an oil processing plant. You have to get your pen and you have to know how to use it, how to do it. Okay, I'm not going to ask you to paint this one, but I could ask you to make this one. Okay, hypothetically speaking, if. Let's go and see the other of the gas that was Christine. Okay, the other plot that, yes?
These MFE and MFD are different wells. The inlets.
I think NF is the name of the field. So it's from this platform, the way it's built, it has the wells, because it has reduced movement, the wellhead is exactly up there and all the wells are deviated.
So the risers that you mentioned are associated with this.
Okay, but in this case you have a few wells from another reservoir, which is down here, and then you have this riser that comes here and then goes up. Okay, so I think this NFE and NFD, they are from a subsea satellite or from.
But the risers there are connected with this inlet somehow. No.
This riser is connected with the green one, you're saying?
Because their riser would be the outlet and top.
Let's see, riser, yeah, exactly these two. Yeah, they are from those two lines. Exactly, you have two risers and they are making gas lift at the base. Okay, that's also something when they start to get, they also do it to stabilize the, and Chidamoyo has a lot of knowledge on that, okay? No, it's true. It's true. So sometimes what you get here from these risers, due to that shape, okay? Let me see, maybe I have a video. I think that's interesting to take a small detour. So. Okay, and again, you cannot say that I told you because that I showed you, otherwise I will be in trouble. So I'm not sure if you see the colors. Do you see the colors? You see the yellow and the
White.
the yellow and white. Okay, transparent. So you see here it's pushing. That no gas is able to pass, it's just increasing the pressure. And you see you have the same thing here, okay, on the going to the platform. It's going very slow. And at some point you see when that starts to go down, whoosh, everything goes away. And then the platform gets a batch of liquid. The whole thing that was filled with liquid gets, the separator gets that batch. That's called severe slugging, but this shape of the riser, why do they use this shape? The boat is going to move up and down, okay, due to the sea. So if you have, there are some other designs of riser which are like that, okay. But if it moves up and down, or if it moves a bit to the side, it will cause a lot of stresses on that bed, okay? So by doing that, it can move freely up and down, and then you have some more flexibility on the system to account for that, for those stresses. So what I was saying is that to avoid that slugging, okay, you inject gas, and then you increase the friction drop, and then by increasing the friction drop, you stabilize the system. Okay. And if you have more questions, you ask Chidamoy. Okay, so let's take now yeah, so exactly you were saying is correct. Okay, I take that gas to inject into this riser and inject here. Okay, and here you see you have a flexible joint because this guy is moving, so you have some flexibility on the system. Okay, so let's take now the second. I'm not sure if there are a few new things on this. Has some numbers, so that's interesting. That's another field which is a high pressure, high temperature field. Okay, but and this probably has, yeah, here is horizontal, but I think it should be vertical. So you see the pressure is quite high, 87. So we should take a break, right? 87. Okay, so then we go to the water. The water is not processed here, right? The water goes together to the second stage and the third stage, which is almost standard conditions. Okay, then let's follow the oil. The oil, just like that, and then you have again a cooler and a meter, and that's the meter that you are reporting to the authorities, or how you split the cake. Okay, what you measure here is exactly what. And here you see this requirement that of the true vapor pressure. Okay, the vapor pressure has to be 0.965 bar at 30 Cs. Okay. And you see, yeah, the conditions. The water processing train is not shown here. The gas, again, comes the gas through the cooler, then through the scrubber and the compressor. And then once more through the cooler, then compressor and so forth. Yeah, then we go to another cooler, another scrubber before. Yeah, I'm not sure. I don't think that's one of these is the dehydration tower. Okay, but I'm not sure. I think one is this one, and this one is the mercury absorber. Yeah. What does it do, the mercury absorber? Okay. Okay, and then finally you see here we have the gas turbine that is driving the big export compressor. Okay, that export compressor has to breach from, do we have pressures here? Yeah, it's close to 87, bit less than 87 to 200 bar. Okay, so that's a huge pressure drop that compressor has to give from around 80, okay, all the way to 210. Pre-condensed bar is 105. Okay, so sometimes in this case we have some conditioning. We are extracting some undesired components from the gas. Okay, but it's slightly simpler than hydrogen. So this is the dehydrator. Yes.
Those are compressors, don't they? And there we have.
This one, yes, it's a compressor. This also compressor.
And that brings a turbine.
Yeah, the gas turbine. GT stands for gas.
Yeah. Could you explain why are we using a turbine and the compressor?
Yeah. The compressor, they have two ways two driving ways, okay, two main drivers. One of them is with electrical motor. So you generate, in a generator, you generate electricity and then you use it to move the compressor. However, and that's is preferred. Or another way to drive the compressor is you put directly a turbine. Okay, you use instead of using a generator to produce electricity, you drive it with a turbine. Okay, but that's, then you will have to use fuel every place you have a compressor. Okay, or you will have to have the compressor in the same place and the same axis connected to the same turbine. Okay, therefore, usually these compressors that are low, they reach a low pressure drop, they are using electrical motor. It's more convenient. But this one, which is huge and is reaching a big pressure drop and is taking the whole rate of the whole field, that is, you use a gas turbine because an electrical motor will be just too big. Okay, you cannot, and more expensive.
So is that fuel gas that goes there?
That get what?
The fuel gas, one that feeds the turbine.
Yeah, the fuel gas that I'm not sure, I don't have it here. Here, yeah, this goes exactly here. Yeah. This goes. Okay, that goes here. Okay, so like I mentioned, maybe I can put you a sketch like that, and you have to say something. I'm going to ask you a question, or you might have to do something like that, depending on the case. Okay, but just be aware that you have to be able to sketch. Okay. Also, when you ask someone how your plant looks like, you in the future, if you are responsible for a plant or you're working on a plant, you have to be able to sketch, okay? Because when you sketch and you say, well, here I exactly have the problem, or if I have a recirculation, or I have some issue, I have to be able to point out where we are. Okay? And of course, when you go to the real field, it's very complicated. You have all kind of pipes going up and down, everything is hidden. But if you understand how the process looks like, it's easier then to point, oh, this is that line, this is that line. Okay? Because if you try to do it in the field, it's very difficult. You have many things on top of another.
Professor,
Yes?
for storage, why normally for oil is used tank, like cylinder, and for gas it's used the sphere?
Well, the pressure basically. The what are you saying? Is you're saying LNG or what?
Yeah.
Okay. Yeah. Well, the main reason is the pressure. Okay, when you have this oil is usually transported at atmospheric conditions. Okay, so you have almost no pressure, just hydrostatic pressure. So you can transport it in cylindric, in how you say, yeah, what is the name in English? It's no, parallelepipedo. How is that name in English? It's what is it? Parallel. But how do you pronounce it? No, but in English also. But how do you pronounce it? Well, you understand what I said. But when we have gas, okay, like for example LPG, the pressure is higher. It's not atmospheric. It's higher. Okay, so sphere is the most efficient shape to keep the thickness of the vessel the smallest as possible. Okay. If you make a sphere, if you make any other, you make cylindric walls, the walls of the cylinder, the two lids, they have to be of a higher thickness, okay, just because of stress. Sphere is a configuration where the stress distribution is the smallest possible, and then the thickness can be also the smallest possible. Okay, so that's why you sometimes use LNG or LPG, you try to use, they are pressurized, they have some pressure, so you have to make them such that they don't use too much material. Okay, so now we are going to do some calculation, okay? But let's take a break first, right? Okay. Okay, so let's say I have this multi-stage. Okay, how many stages okay, and I can just take out cooler, compressor, whatever. I'm just doing, like that to make my life simple, and that's what we're going to model later in DWSIM, this process. Did you use any process simulator before? Like HYSYS or Unisim or no? Okay. So I hope it goes fine. Okay, so if we have, let's say here we have a molar stream. Okay, let's call it now, we are going to talk a bit about moles. Okay, you have here molar stream of the well. Okay, and now that molar stream of the well will be equal to the molar stream of C1, molar stream of C2, all the different components, right? I sum the moles of all components, and that gives me the total amount of moles. And I'm going to get here also the moles of also all the components, okay? Let's call it oil or liquid, and liquid I of methane, etc. So if I make a plot, the following plot, okay, and I put first every component here, C1, C2, C3, C4, C5, C6, okay, and the rest, okay, I have many more than C6. And I'm going to plot here the ratio, okay, between the moles that are in the liquid compared to the number of moles that are in the well, okay, at the inlet. So let's say here I had 20 moles of C1, and here I got just 1, that will be the ratio, okay? Or if I had here, I don't know, 60 moles of C6, and here I got 50, it will be 50 divided by 60, okay? If I use a single stage, okay, if I just use one separator, not like what I have here, I will get C1 and C2, they like pretty much to be in the gas phase. Okay, so they will be almost, very little will be in the liquid, almost nothing. And C5 to C6, here if we have 1, okay, these guys, they like to be in the liquid. Okay? But all these guys in between, they don't know really where. They go where the party is best. Okay, so if you use a single stage, most of them will go to the, it will be something like that, okay? Most of them will go to the gas. When it's 0 is that it goes to the gas, okay? The gas is the opposite. So this is if I have a single stage separation. Now if I have a two-stage, it's like I have more time, okay? I have more time to convince these guys from C3, C4. Well, you know, it's also good in the liquid. You should spend more time in the liquid. And what you are getting is maybe something like that. Okay, so that is for two-stage. Okay, multi-stage, then I start to get something like that. More of those C4s and C3s into the gas. And if I could use an infinite, okay, if I could use an infinite number of, and then I will be, you know, trying just my best to be like that, okay? So infinite. So that's the main reason why we have multi-stage. Okay, we just try to make these guys that are still, they can go one side or the other, we want to make them be in the liquid. Okay, so that's why I typically have a multi-stage. Of course, I have to reach to there is a limit on the cost. After some stages, the increment, the change between one and the other is not so much, is not so relevant. And having more stage, it adds complexity, okay? And it adds cost. I need more separators, I need more pumps, I need more compressor, more cooler. So usually that number is something up to 4, sometimes 5, okay? But I don't go higher than that. I use usually 5. Usually something between 1 and 5, and a normal number is like 3. So there are a few things that we have to be careful on, or that we have to, and that we're going to look at here. Okay, one thing is the effect of a high pressure. Okay, then you have the effect of a medium pressure. And the third thing that we are going to look at is the sizing. Okay, how do you perform the sizing of the separator? And that we're going to talk tomorrow. Okay? So first, the effect of high pressure. If you plot the GOR, let's say, okay, let's say that we have, for this experiment, we have a fixed inlet, okay? We have certain mass flow, okay? That's fixed. And then I will start to change the pressure of the first stage, okay? This will be the pressure of the first stage. Typically what I get is that as I increase it, it goes down and then it starts to go slowly, slowly up. Okay? When that's the GOR, okay, that's the Q gas and that's the Q oil, and that's the ratio between GOR, Q gas divided by Q oil. Remember, I'm keeping the mass flow fixed, okay, somehow. I'm saying it's always coming in the same thing to the separator, but I'm just changing that pressure to see how it changes. So is it better to have high or low GOR? Low, right? So in reality, I would like to be here, ideally, right? So that means that, okay, that I need a high, relatively high or higher pressure. Okay, after that, you have an increase which is very, very like slow. Now, what is the problem of using a high pressure for the first stage? So it tells you high pressure gives you more oil. Okay, high pressure, more oil. Now, what is the problem of using high pressure for the separator? If we make our equilibrium right, we have our well where we have that is close to the separator. Okay, if we increase that pressure, what will happen with the rate, with the equilibrium point?
Decrease.
It will decrease. Okay, so even though we increase the pressure, that's fine. We're recovering more oil. That has a counter effect on the amount of rate that I get. Okay, because here I have my IPR, and then I have the TPR. Okay, what happens if the pressure? Another exam for exam question. So what happens with this guy with the TPR when the pressure increase? It goes like this, right? Like this. Okay, that's for P wellhead pressure higher than this guy. Okay, so it's not always, even though it's something that I can use to improve, okay, the GOR to get more oil, it's not something that I normally like to change too much. Okay, I cannot take it very, very high because otherwise I'm reducing the rate. Okay, the mass flow that I'm getting here will be reduced. Okay, so that's something that is important for, usually this is important for gas condensate, okay, when I have very high GOR. Because gas, if you remember the curve for gas, it was relatively, if I have a big size tubing, right, it was relatively flat, okay? Therefore, I can increase, I don't lose too much in rate in the equilibrium, but I will get a lot in oil, okay, by changing that pressure. So for gas, sometimes this is an issue, but normally I don't change, or I like to keep it as low as possible for oil, when I have oil. Now, the medium pressure separator is another issue, okay? In that case, the pressure of the first is already fixed, okay, which is, a number that gives you high production. But the pressure of the second, the pressure of the third is also relatively fixed, okay? It's related to to the metering, is related to other things. Okay, so this one is more or less I cannot change. This one is also I cannot change. But this one I have to decide. Okay, if I use it close to HP or close to low P. So in that case, and we are going to try to do this exercise, hopefully we will have time. Again, you can plot the GOR versus the pressure of the medium pressure separator. Okay, and you can have to change it between the high pressure and the low pressure. Sorry, it's the opposite. The low pressure and the high pressure and the low pressure. And again, it gives you a curve, something like that. Okay, you see the tablet is behaving wrongly. So in that case, we can do something. Medium pressure doesn't affect at all the rates, doesn't affect at all the equilibrium, nothing, but it affects very much the GOR. So what we do is that we run a case with different pressures, okay, until we reach a minimum, then start to go up, and then we say, well, this is our medium pressure of the separator. Okay, we hope to try to make an exercise on that. Now, how do I study this, a separation process or process simulation? So what tools do we use? How to study or how to model separation process? Okay, and in that case, we need what is called a fluid model. Okay, something that represents the fluid, and we cannot use any more black oil. Okay, black oil, remember, we have a transformation, but we are not looking at the plant. Now we are looking at the plant, what happens inside the plant. So for that typically we have two choices. Both we are going to cover here in class. One of them is using K factors, or another option is using EOS, an equation of state. So we're going to talk a bit about this first. We're going to make an exercise, and then for this one, we're going to use the software that I told you to install. Okay, first the K factors. So if you make a plot, okay, you have, let's make some nomenclature first. Zi is the composition of the mixture. Okay. Of I is methane, also it can be ethane. I is the component, okay? Okay. This is mole fraction. Okay. And then I have the oil and the gas, and we know already how to call them. I think we introduced the nomenclature in a previous class. This will be mole fraction of component I in the liquid, and Yi is the same but for the gas, the mole fraction of component I in the gas. And Z is if you look at the whole thing. Okay, Z, if you sum up all the mole fraction, all the moles that you have in the gas and in the liquid, and you divide by the total number of moles. Okay, so something very, very interesting. And that's an approach that many people were working in the industry for a long time, especially when modeling processing equipment. Okay, so they plot the log, okay, in log scale, the Ki of the component, which is Yi divided by Xi. Okay, and they did this plot for a constant temperature, okay, constant. And here they plot the pressure. again in log, and this is also log. So you have here 1, 10, 100. Here we have 1 to the minus 1, 1 to the minus 2, 1 to the minus 3. Okay. And what they saw was extremely interesting. They saw that some components, light components, the line is here. Okay, this is for C1, maybe C2. Okay, the line makes that behavior. Okay, they took a mixture and they measured the mole fraction, and they saw that in the mixture, if they divide for different pressures, taking the different pressures, they see that it has that behavior. Okay, just a straight line in a log-log flow. Here you have, for example, C4 goes a bit more like that, and if you have C10, it's go even lower. Where the slope is here is -1. Always for all of them was -1. And that was a big thing because they had the ratio between the two at the intersection, okay? When they intersect here, okay, where it's exactly 1, you can say that Ki equal, this pressure here is the vapor pressure, and is PV at that temperature divided by the pressure. But I think you have to use log someplace, so that's I think it's the log. Let's check the book. Okay, but you see, you have here, you have the tables, okay? You have this, the K, how it looks like. Okay, and they could measure that K, but the thing is that it's a constant, okay? So it doesn't matter. For high pressures, you will start seeing this curvature for high pressures, but for low pressures, yeah, so where is the equation? Okay, Ki, P, vapor pressure, no, with no log, it was correct. Ki, vapor pressure, okay? So the curve doesn't do, so it goes like that, and then starts to be curving, okay, till they reach some point. Okay, the same thing here, the same thing here. Okay, but for production and reservoir, we are usually in this range, okay, for production and reservoir. But for processing, a big thing was that we are exactly where the range is linear, okay? So that's for surface processing, usually. Therefore, we can use that K if we know the vapor pressure at that particular temperature, and we know the pressure, we can calculate exactly the splitting. And you're going to see now why that's very important, okay? If I have the way, for example, methane, ethane, whatever the components you have in the mixture, how they split. How much goes to the liquid, how much goes to the liquid and to the vapor. So let me just take, and you see you have different Ks for, these are different temperatures, okay? And you have different ethane, propane, butane. Okay, but let me ask you something. why do we have the close, okay, why all of them come and converge here to that pressure? Okay, we make it here. Okay, from this point, what happens after this point? No more vapor and no more liquid. Okay, after this point, we have just one phase. And what is that point? This point is the critical point. Okay, so for this, exactly for this case, this temperature is the critical temperature. Okay, and all of them converge to the same point. Okay, when I'm not at a temperature that is not the critical temperature, basically the plot stops existing from some place. Okay, after I reach what you will say the bubble point PB, okay, after that point all of that stops existing. Okay, so the curve will only be all the way, all of them will converge to the same pressure only when that temperature is the critical temperature. Okay, that's where all the points will converge. Okay, and for that, we are going to use here in class, so that's what we are going to use, okay, just this range, okay, the range where the equation is linear. And we are going to use an equation that is called Wilson equation. And I think it's, let me take it from here. Okay, that equation is the one that we are going to use for K, and then we're going to use this DWSIM. Okay, but we had tables of measurements made for different compositions, for different mixture. So let me just make a comment here. For this region, a comment that I forgot. In this region, when it's curved, okay, the K becomes a function not only of pressure, but becomes also a function of Z, okay, of what other components you have. So it matters if you have 1% of methane or if you have 10% of methane. So that curve is not so easy to predict. It depends on the rest of the components. But for this range, it's fairly easy. It's just a function of pressure and temperature. Okay, so that's the equation we're going to use, which is Wilson equation. And that equation uses the P reduced pressure of the component, okay, which is the pressure that we have divided by the critical pressure of the component, and the reduced temperature of the component, temperature divided by the critical temperature of the component. So we need that, okay, that you see we have. This is the eccentric factor, another property of the component. Eccentric factor. And yes, and we need also one more thing, that is the convergence pressure. We're going to use this expression. Okay, the convergence pressure is like a tuning parameter. Okay. It's a parameter that I used like a tuning parameter. In reality, you assume basically that the curve, all of them will join at the critical point, okay? But only for the critical temperature. For all other temperatures, it will reach only up to the bubble point, okay? But what I do is I prolong the curve until they join, and that I call the convergence pressure. And I use that as a tuning factor. But don't worry about it, it's just a tuning factor. Okay, so what do we do with the K? Okay, so that's the main question. You say you're talking about K and K, what can be done with K? What do we do with K. Okay. So let's see, how many equations we have? We know that the sum of yi has to be equal to 1, right? We want to find xi and yi. These are the unknowns. Xi and yi are unknowns. Okay, and I have Zi is given. Okay, Zi is given the mixture composition, and I have also the K. Okay, is calculated from correlation. So I want to see if I have enough equations to solve how much is xi and how much is yi. So how many equations do I have here? 2 equations only, right? Okay, I have 2 equations. How many unknowns I have? So if I have n components, right? Then I have, are you sure? So we need xi, right? Here we have n unknowns. And we need also yi. Yes? If we have, let's say 3 components, right? So we have the mole fraction of component 1 in the vapor phase, the mole fraction of component 2 in the vapor phase. Okay, if we have 3 components, if n equals 3, we have x1, x2, x3, and y1, y2, y3, right? So we have 6 unknowns. Okay, so we have 2 times n unknowns. But with the k factor, how many additional equations we have? K1 equal to y1 x1, K2 y2 x2, K3 y3 x3. So we have 3 equations, 3 additional equations. So here we have 1 equation, here we have 2 equations, 3, 4, 5 equations, right?
Yes.
And we have 2 times n. We need 1 more equation, right? Has to be the same number of equations and unknowns. So what else do we need? We know also that set I is, if we introduce now a new factor, FB times YI, this is the vapor mole fraction. Okay, which is the number of moles of vapor divided by the vapor plus the liquid. Okay, and we know that it has the following relationship: 1 minus FB times XI for each component. Okay, so here we have 3 more equations with 1 additional unknown. Okay, and then I have all the equations I need, right? I have 1 more unknown, so I have 2 times n plus 1. But I'm getting 3 additional equations. Okay? So I can solve the system. Okay. So to solve it, okay, I'm going to say how we are going to solve it, because it's a very complicated problem, okay, to solve it. So I'm going to say, this is a method to solve the system of equations. And the goal is to avoid iterating with the composition xi, okay, or yi. I don't want to iterate because they will be just, if I have 10 components, 30 components, it's just too challenging to choose all of them. So I just want to iterate just with FB, okay, just with one. But for that I have to do some massaging, okay? So the massaging I make, starting from this equation, set I, FB, yi, plus 1 minus FB, xi. I substitute ki is yi, xi. I substitute this guy here, so I get FV xi times xki, and then I take as a common factor xi, sorry, here I'm missing this part, okay, and then I use xi as a common factor, so I have FB ki minus FV plus 1, okay? And then I express xi as set I over FV ki minus FV plus 1. And now I'm almost very close, okay? You see, in all the term on the right, I took away. I don't have any more yi, xi. I don't have anything, okay? Now, I use the equation that sum of xi is equal to 1, and the sum of yi is equal to 1. Therefore, the sum of yi minus xi should be equal to 0, okay? If I take as a common factor xi, okay, sum of xi, here I get k minus 1, right? And then I can just substitute this guy here. And then I have the sum of set I times ki minus 1 over fv ki minus fv plus 1. Voila. Okay? And that's called the Rachford-Rice function. Okay? And these two guys, they were in the 50s trying to find, how to solve this complex system of equations, because if I have more components, it becomes more complex. I don't want to iterate. They tried, it's very complicated. So they try to sum up to introduce one equation in the other, such that I end up only with one equation where I have to iterate with FB. So here I have to find, remember, set I is an input, ki is also an input. So the only unknown in this equation is FB. That's the only thing I have to find. Okay? So let's do that exercise, okay? To try to see if we are lost or are not lost. Okay, class exercise, and is day 10, okay? Flash calculation exercise. It should be in the class exercise if you don't have it, you have to go to my website to get it.
No.
Okay, so first look at the top part. Okay, we have the convergence pressure, and then we have the critical properties and the eccentric factor. That's to calculate what? The K, right? This Wilson correlation. Okay, if you go back to the notes, we know 10. It says day 10. Okay, this correlation that I'm getting the eccentric factor, the critical temperature, critical pressure, and I need here, so that's not the right equation, this is the right equation. That we are going to use, copy, paste it here. Okay, so with that I'm going to get K, and then after that for pressure and temperature, and after that I can start to make this solving process. Okay, so let's do that first. And here you have the separation process, high pressure, medium pressure, low pressure, their pressures and temperatures, and you have the composition at the inlet of the first stage. And we are going to calculate all of them. Okay, and then we're going to do it with this simulator. Okay, so we say we start at the first stage, 50 and 70. We take the composition 0.5, 0.2, 0.3. The first step is to calculate K, Ki. So for that we Alt F11. We are going to use the equation called Ki Wilson modified. Pressure in bar, temperature in Celsius, but the critical temperature is in Kelvin. Be careful. Okay, so let's use that equation, Wilson modified. So let's call that equation user defined, and it should be with W, Wilson. No, it should be with K, sorry. K Wilson modified. Pressure that I have is always going to be this number, and I block it. The pressure that I have. Temperature is in Celsius. Okay, I put it here. I also block it. Convergence, this tuning factor that I use to reproduce all of these charts. I go up, or it should be, yeah, it should be up here. C, yeah, I can, and I have to block it also. Okay, C3, block it. Now, the critical property of what? The critical temperature of the component I have to the left, the methane. Okay, so I have to go up, and methane, the critical property is here, and the critical, sorry, it should be the critical temperature is in B, critical pressure is in C.
So what is the unit that you use for the...
Yeah, they are consistent. It's bar should be the same unit, but this is in Kelvin. They are consistent. And then we go back and we have the eccentric factor.
For the critical, it's in Kelvin.
Yeah. But don't block it. We are going to drag now K to the rest. Okay, so we want that we drag it down. It will use now the critical properties of propane and N-decane. Okay, so pressure, temperature, these are blocked. Convergence pressure, this tuning factor, this is blocked. Critical temperature of the component, that's not blocked. Okay, pressure is not blocked, and eccentric factor. And I get a K of 10. Okay, that means that, and this is for methane, okay, that the mole fraction in the methane is 10 times bigger than the mole fraction of the methane in the liquid, which makes sense, okay? That means I have much more methane in the liquid, in the gas than in the liquid. 10, and then I copy and I paste down, okay? And that gives me close to 0, which again makes sense, okay? I have much more decane, the heavy component, in the liquid, okay? Remember, this K is Yi, the mole fraction in the vapor, divided by the mole fraction in the liquid. Now, I want to calculate this Rachford-Rice, okay, which is a sum. How did we say? It's a sum from component I1 to N of all of these terms. So I'm going to calculate that term for each component, okay, and for each component, and then I'm going to sum them up. The sum has to be equal to 0. You see here, that's the mole fraction of vapor, okay, and that I have to assume, that's the number I have to change with solver, okay, so we have 0.1 as a starting point. So let's see, how do we call the Rachford-Rice function? It's called Rachford-Rice term, okay, RR term, so that's how we have to call it. User defined, now RR term okay, is here. So set, I don't block it. I want when I drag it down, it will use the other one to the left. K, no, sorry, set. First is set, so it should be B. Then is K, and then is FB, which is here, and that I should block. Okay, you see the term is 2 point something, and then when I copy and I paste, okay, and it gives you 2, which is not correct. That should give you 0. Okay, so that's the number we have to drive to 0. Ki and Yi? Sorry? Xi and Yi? Well, Xi, right, we can calculate from here, from this equation, right? If we have the FB, and that equation is programmed for you here. And Yi, how do I calculate Yi?
It's a relation.
It's Ki, right? Ki is Yi divided by Xi. So I just multiply Ki times Xi. Okay, so let's fill first Xi. Function, we are using many functions here. Xi the last one. Okay, Xi, and that's using set. Do I block it?
No.
No. Volume fraction, I block it? Yes. And Ki, block it?
No.
No. Okay. Okay, and then I copy and I paste. Xi, you see, should give you equal to 1. That's the sum of all of them. And it doesn't give you equal to 1. That means I don't have a solution yet. Xi, the Yi, sorry, that is Xi times K. Okay? And that actually gives you a number that doesn't make sense, even. Okay, it should be a fraction. That number should give you also 1. Huh? Xi? This one? Xi is set, not blocked, FB blocked, and Ki not blocked. Now, what do we use? Solver. Yes, we don't know, we don't want to start trying numbers randomly, so we use solver. So go to data, solver, and we ask our mighty solver, solver, please drive the sum of all of these k's has to be equal to 0, right? So it's D26 by changing what? FB, okay? And that was the whole point of these two guys that were very clever. They say, well, if I put all of these equations together, I try to find a way that I just have to iterate with one number. Okay, very clever. Otherwise, we have to do it, with all compositions, with xi, everything. To the constraints,
Yes. Yes.
this fraction,
No, excited enough as one.
no, but let's say this FB can be only between 0 and 1, right? You can have either 100% vapor or 0 vapor, but you cannot have a negative number. So let's add that constraint, okay? Add, and we say this number has to be less than 1. Then we click add to add one more, and then this number has to be greater or equal than 0. Okay, just between 0 and 1. And then we click solver, do your magic. Okay, and it converged. Doesn't converge? Uh-huh. Here, very different. Huh? Who is? Maybe it might be me that I am here. Okay. So. Now, what is the composition entering the medium pressure separator? What is the composition entering the medium pressure separator? If we go back to our notes, okay, or I go back to my notes, whatever is centering the medium pressure is actually xi, right? This is yi, this is xi, and what is centering the medium pressure is just xi. okay, from the high pressure. Okay, so what I have to write on the table has set I has to be these guys here. So I copy, and be careful, I have to paste special, but not only values, but also transpose. Such it will copy, paste exactly like that. I select, now I go for the second phase, okay? I was in the first stage separator, I now go to the second stage separator, okay? Whatever is entering is the liquid from the previous stage. So I copy Xi, okay? I place myself in the first cell, and then I say paste, special, values, and transpose. Because I want to copy transpose. Not on this direction, but I want to paste on this direction.
Sorry, this next time it's the oil.
Oil, yes. Oil, only the oil is going to, only the oil from this phase is going to the second stage. Yes?
Why I think so gas?
Yes, for gas. Now, I want to make the calculation for the second stage. What do I have to change? I have to copy the pressure, paste it here. I have to copy the temperature, paste it here. Something's wrong. I have to copy the set, right, from here, the inlet set, and I have to paste it here. But again, I have to be very careful. Paste, special, values in transpose. Okay? And now I'm ready to solve for the second stage. Okay? Here I have, here in this section here, all this section here, I'm making my flash calculation, right? I'm making the calculation of how the vapor and the liquid split. Okay? So here I have to put the temperature of my separator, the pressure of my separator, and the composition, inlet composition to my separator. Okay? Here. And by solver, I'm calculating the equilibrium. Okay? So I did it now with these two numbers and this composition. I just did it now using the solver. And I find xi and yi. Yes. Okay? Now, for the second stage, what is going to come in is the oil from the previous stage. Okay? And the oil is xi. Okay? So I have to copy this xi, paste it here, just the values. Okay? And then I have to say, well, I have to change. Now my separator is second stage. Therefore, the pressure and temperature are different. I copy, paste here, copy, paste here. And then this set that I have, the inlet, I have to paste it here. Okay? So again, I have to copy this line, paste, values, and transpose. And then I run solver once more. The same way, exactly the same numbers solve. Fine, perfect. Now I have, again, the same thing. Copy, paste for the next stage. Okay. You're going to see thankful when we saw the simulator, you don't have to do anything. Okay.
We change the temperature.
Change pressure, change the temperature.
This is the 35.
Yes, pressure with pressure, temperature with temperature. One time you have to copy these guys, three
Guys, with the
here, but you have to transpose with value. Transpose. Okay, and now you run this over once more. You got it? Or you can do it for the next. Okay.
Não, explica. Depois de ter aqueles ali, já fez os dois. Depois da lista de pessoas, é isso? Eu preciso por esta linha, 50 por esta linha. Ok, depois tiveste estes valores.
Não.
Pegaste este aqui, este por
Exatamente.
Ok, depois eu pôr aqui,
Por ali, pelo sul.
mas pagar só para aqui mais.
Não sei perguntar, não vai sair pelo sul. Eita, você vai.
Isto aqui é
Não sei, pode ser uma
And it's ending is not on this article. It's ending on this second one.
Yeah, then now the lower pressure, okay, which is just atmospheric, then we copy these results
There.
here, okay, and now you calculate the equilibrium. Okay, so oh, it's already past the time, so okay, so the conclusion before, to close our session, we continue tomorrow. The conclusion is basically mass balance, okay? We are doing mass balance. We know that in the range of low pressure, there is a linear relationship between the moles of gas and the moles of liquid. We use that to make a mass balance, okay? This mass balance is very complex. People have tried to solve for many times, didn't manage. Came these two guys, they say, well, we can solve it in a different way, such that you don't need to iterate with the mole fraction. We just need to iterate with one value, FB. And we solve stage sequentially, okay? First stage, second stage, third stage, and we calculate compositions, okay? What do we need compositions for? To calculate properties, okay? How much liquid, how much gas, density, we need to calculate how much fluid. So this is a very challenging exercise, but just to show you that when we use tomorrow the simulator, now you think about how much effort this simulator has, okay? Because it has to program for every separator we have, had to make, very demanding process many times. Okay, but so you know it exists, you know how it is done, but when we use a simulator, we don't have to do it ourselves, okay? The simulator is doing it for us. Okay, so we close our session today. Tomorrow we are going to work to make the same example, but with this software, DWSim. I will try to do it step by step. And then we take a short discussion on sizing, okay? What is important to define size of the separator? And with that, we close the course, and then, I think you had already enough information for the whole semester. Okay, so see you tomorrow.